All right, moving into some rules for variances, and when we say variances, we know that that also means that they're going to apply in a related way to standard deviation due to the relationship between those two statistics. We have some rules for variances, but we have to talk about something that's going to be extremely important in determining these rules, and that is independence of the two or more random variables. So when dealing with rules for variances, you have to be very careful to check for independence of random variables. Independence. Yep. Becomes a distinct issue. So this is going to be built into the formulas. If things are independent versus if things are dependent, they are going to operate slightly differently. So let's talk about if x and y are not independent. So if x and y are independent, the rules that we just talked about for the mean hold, and in fact we'll be able to easily verify that the variance rules hold. It's when x and y are not independent that we have to be a little bit careful. So x and y are not independent. We have to treat this as a bivariate set of data, which would mean that we could like make a scatter plot of the random variable x versus the random variable y. And if things are moving together, meaning that x is influencing y or y is influencing x, then there has to be something about the correlation known between x and y. So the correlation between the two variables is going to be given to you. So in this type of class, so this is not an advanced stats class, you will be given the correlation if the two variables are not independent. You will not have to find it on your own. It'll be stated right in the problem. You'll be like, why are they telling me about the correlation? It's because you need to use it. And we're going to be talking about population data again. Remember that mu sub x and mu sub y are population data statistics. So we're going to be talking about the population correlation. So instead of using R, which is the sample correlation, we're going to be using a new statistic called rho. So rho kind of looks like a P, but it's not really a P. You saw how I just drew it, so it's not how you would typically draw a P. This is the population correlation. Population correlation. All right, so be on the lookout for rho or for the population correlation when dealing with variances and standard deviations. To do a little investigation here, I'm going to define two very simple random variables. We're going to say we have a random variable x, which takes on the values of 2, 3, and 4, and a random variable y, which takes on the values of 5, 7, and 12. And we are going to be interested in generating a new set. We're going to call it set z, which is the random variable x minus the random variable y. And for this, let's also assume that there are only 3 elements of each of the two sets. So let's assume that they are occurring with an equally likely outcome. So the probabilities of occurrence for 2, 3, and 4 are 1/3, 1/3, 1/3, and for 5, 7, and 12 also 1/3, 1/3, 1/3. So the first thing I need to talk about is how you actually combine sets of numbers. It's not so intuitive for this one. So if I want to generate the set z, which is x minus y, one might think I would do 2 minus 5, 3 minus 7, and 4 minus 12. And I would get a new set z that also has 3 elements. In fact, that's not how it works. Set z is going to be generated by taking every element in x and subtracting every element in y from each of the individual values. So I have to do 2 minus 5, 2 minus 7, 2 minus 12, and then I have to do the same for 3 and 4. So I'm going to generate a set z that has 9 elements in it. So the first thing I want you to do is pause the video and generate set z. Alright, so these should be the 9 elements you get for set z. Again, just done by subtraction. And let me tell you right now that we're doing this one example out so that you will be able to use the shortcuts and understand where they come from. This is not the process you would have to do to generate these new sets each and every time and to talk about their means, standard deviations, and variances. But while we're here, let's talk for a second about mu sub x and mu sub y. So if x and y have random variables that have equal occurrences, If I want to talk about the average x value, it really is just the sum of the three numbers divided by 3. So 5 plus 4 is 9, 9 divided by 3. You should get mu sub x to be 3. And then 12 plus 12 is 24. Mu sub y should equal 8. And I want to find mu sub z. What is mu sub z? Well, to generate mu sub z, all I have to do is go to my new set z, which I just created, all of these values, add them up, and divide by 9. So if I take and add them up, I should get, I believe it's negative 45. If you add all those up, and if you take negative 45 and divide it by 9, you get negative 5. And we had an addition rule earlier on for finding the sum of random variables. It should be no shock that if you want to find the difference of random variables x and y, that mu sub z should just equal mu sub x minus y, which is mu sub x minus mu sub y. So there's really no need to generate the set to find the negative 45. If you know mu sub x and you know mu sub y, mu sub z is just the difference of those two. If it were an addition statement, it would be the sum of those two. To find the variance, though, that's a little bit more difficult. So I'm going to pause the video right now and write out the steps for finding the variance, and then I'll come back and talk about them. All right, so as you look at what I did here, I generated the variance for each of the random variables x and y. So by taking the individual values and subtracting their means, squaring, summing those up, and then because they were equally likely, instead of multiplying through by a third each time, I can divide by 3. And I get that the variance for x takes on a value of 2/3, and the variance for y takes on a value of 8 2/3. And I want to figure out a way to generate the variance of z, this new set x minus y. So if you were to just hypothesize right now, logic would tell you, okay, the variance of x is 2/3, the variance of y is 8 2/3. I'm looking for the difference of the random variables, so maybe I should just subtract those two values and do variance of x minus variance of y, which would be 2/3 minus 8 2/3, which would give you a negative variance, but let's just call it 8. That the difference between the two is about 8, so the variance for z should be 8. I'm going to pause it one more time, and I'm going to generate for you the variance of z using the 9 elements of z and mu sub z, which is negative 5. All right, so here it is. Here's all the work done out. I'm dividing through by 9 due to the 9 elements that are equally likely. And lo and behold, I get that the variance of z is 9 1/3. Not 8. In fact, it's the sum of the two variances from x and y, not the difference of the two variances, which would maybe make sense if we were doing x plus y, but why does that make sense if we're doing x minus y? And, you know, it kind of goes back to this old adage of this idea of pouring water into and out of a pitcher. If you are pouring water into a pitcher, so you're adding two things together, as you pour water in and you're trying to get to a certain value, there's variance associated with you pouring water into that pitcher. So maybe you overpour, maybe you underpour, whatever it is, you have to keep pouring to get to where you want. And if you overpour, you have to then pour water out of the pitcher. Well, if you pour water out of the pitcher and you don't get it exactly right, you have again increased the variance in the amount of water in the pitcher. So mathematically, it doesn't matter if you're adding or subtracting to that pitcher, you're always adding to the variance of that pitcher by each subsequent change that you make. So when we go on to the next page, you're going to see that the rules that we're going to establish, again, don't really make sense, but they make sense if you think of that story. All right, so here are the first two rules, and it's very simple because it's actually the same rule. If you are taking the variance of the sum of random variables, then you are just going to take the sum of their variances. So this rule up here, if you're doing x plus y, variance of x plus the variance of y. If you're taking the variance of the difference of random variables, it doesn't matter that you're taking the difference, it is still the variance of x plus the variance of y. So it doesn't matter if it's a subtraction or addition, the random variables will always be the sum of the variances, it will never be the difference. So there's a set of formulas that you need to know moving forward so that you don't have to recreate sets. You can just use some shortcuts. Now, this is under an assumption, and the assumption here is that x and y are independent. So we talked about row on the other slide, so here is where row comes into play. If x and y are not independent, then the correlation is going to be given. And that correlation, again, is that funky looking p thing, which we call row. So if you are looking at the variance of x plus y, when the two values are not independent and there is an association between them, it's going to start out the same, variance of x plus the variance of y. But then we have to build in this relationship between x and y, and this is not something that we're really going to go through in class to try to prove, but you're going to take 2 times the row value times the standard deviation of x times the standard deviation of y. When you do the difference of the random variables, you're going to start out the same way, the variance of x plus the variance of y, but now you will subtract off 2 row sigma x, sigma y. And the cool thing is, kind of like when we did OR statements, when we had to worry about disjoint and non-disjoint intersections, if there wasn't an intersection and we used the p of a plus p of b minus p of a and b, the p of a and b became 0 and you didn't have to worry about it. If these two random variables end up being independent and you didn't know about it, doing this addition or subtraction will not change the variance of x plus y or x minus y, because for independent random variables, row is equal to 0, and this entire term becomes 0, and you're back to what we have up here. So those are the formulas that you need to know for the rest of Chapter 7. Look for using them when doing the homework problems. You shouldn't have to be recreating entire sets. You should be able to make a linear transformation on the mean. You should be able to combine variances in a way that you don't have to recreate sets to find variances. All right, so good luck on that, and that's the end of Chapter 7. I have one last thing to say. Again, I just want to say thank you guys all from the bottom of my heart for the little party that you guys threw. It made me very happy. So I'll remember that for a long time. So best of luck, and I'll be in touch again later on. Bye.